Good afternoon, everyone. We are going to get started in just a second, but feel free while you're waiting to just type in the chat where you're tuning in from. Guessing we'll get a lot of Maryland folks. I know we have Dr. Holtz on campus in College Park today, but feel free to just let us know in the chat where you're tuning in from. New Jersey. Oh gosh, someone in sunny Florida. Welcome, Catherine. Chicago, awesome. Another College Park. Centerville Hall, oh, awesome. Thanks, Dr. Holtz. We know exactly where you are. Ellicott City, Gaithersburg, lovely. Charlottesville, Howard County, Silver Spring, this is so great. So all East Coasters so far. Everybody's right around lunchtime. Laurel, hi, John. Thanks for joining. Westchester, Pennsylvania. Welcome, Steve. Happy to have you here.
Greetings, Terp alums. Can you remember the feeling of sitting in class, captivated by a professor's passionate teaching that sparked your curiosity? Well, today you'll get to experience just that all over again. Thank you for joining Alumni Association's new lecture series, For You. Through these events, we are excited to share with you the groundbreaking research from our world-class faculty who are helping to solve the grand challenges of our time. Now get your notepads ready and don't be afraid to ask questions, but don't worry, there won't be any pop quizzes at the end. Welcome back to the classroom and go Terps!
Well, good afternoon and welcome everyone. My name is Ellie Geraghty and I'm the Director of Alumni Career Programs for the University of Maryland Alumni Association. We are so excited that you're able to join us for today's faculty speaker series with Dr. Tom Holtz, Paleo Talks from Ballerinas of Doom to bone-crushing bruisers. We have a lot of information to cover today, but we will take questions throughout the webinar. Feel free to submit any questions that you have using the chat function on the bottom of your Zoom panel. This webinar is being recorded, so by participating, you acknowledge and consent to your image, likeness, or voice being recorded. Speaking of recording, a recording and slides from today's webinar will be available and shared with you following today's session. You may also access the closed captioning feature by clicking the CC button at the bottom of your Zoom panel. Okay, so a little bit about Dr. Holtz. Dr. Thomas R. Holtz Jr. is a principal lecturer in vertebrate paleontology at the Department of Geology at UMD. His research focuses on the origin, evolution, adaptations, and behavior of carnivorous dinosaurs, and especially of the Tyrannosauroids. He received his bachelor's in Earth and Planetary Geology at Johns Hopkins and his PhD from the Department of Geology and Geophysics at Yale. He's also a research associate of the Department of Paleobiology of the Smithsonian Institute National Museum of Natural History and serves on the Scientific Council of Maryland Academic Science. Also, he's the creator and faculty director of the College Park Scholars Science and Global Change Program. He's been a consultant on museum exhibits around the world and on numerous documentaries. He's the author of the award-winning many popular audience books. He's the current editor of the Life of the Past series at Indiana University Press. He receives the 2018-2019 Provost Excellence in Teaching Awards for professional track faculty. Dr. Holtz, we're so excited for today's session, and I can't wait to hand it right over to you to get things started.
Great, and I'm glad to be here. So let me start to share my screen. There we go, and get it up and running. And so, yeah, I want to thank Ellie, and I want to thank the Alumni Association as a whole for inviting me to give this talk about the things that I love. So that I can share some of this research that's ongoing both from myself and from colleagues about the changing ecology of tyrannosaurs through their life cycle, from ballerinas of doom to bone-crushing bruisers. So as Ellie just described, my name is Tom Holtz. I got my PhD at Yale, and I've been teaching in the Department of Geology here since the spring of 1994 and full-time since the spring of 1995. So I've been here a while. I started working with the College Park Scholars Program in the fall of 1999, and I'm still with it today. It makes me the longest running faculty director in Scholars, actually by far. And I have a research affiliation with the Department of Paleobiology at the Smithsonian, and I serve on the Scientific Council of the Maryland Academy of Science, which, if you're not familiar with that, that's the organization that runs the Maryland Science Center in downtown Baltimore. It's one of Maryland's oldest scientific institutions. So my primary research focus is on carnivorous dinosaurs, as Ellie said, and these are a number of the recent papers of research that I've been involved with, some of which will be featured in today's lecture. I'm happy to talk about some of the others if there's time. And one of the nice things about doing paleontological work is that there are extremely talented paleo artists out there, people who can reconstruct creatures of the ancient world and use them to bring your papers to life. And these are the illustrations that some artists have provided relevant to the papers I just showed on the previous slide. And I want to thank them for allowing their work to be shown and for giving a great way to visualize this kind of work. So I am indeed a researcher on dinosaurs. I'm a dinosaur paleontologist, and despite the fact some of you might be thinking, well, isn't that redundant? No, in fact, the vast majority of paleontologists don't work on dinosaurs. In fact, the vast majority don't even work on animals with skeletons. They work on plants, they work on marine shellfish, they work on all kinds of organisms. And even among those of us who are vertebrate paleontologists, who work on creatures with skeletons, most of us don't work on dinosaurs. But some of us do, and I happen to work on dinosaurs, and I happen to work on the most famous of dinosaurs, Tyrannosaurus rex and its kin. So, I go to museums to study them. I collect dinosaurs and other fossils out in the field. After all, you don't know in advance what you'll be finding. This is me working on the bones of a mid-sized beaked dinosaur in southeastern Montana, part of an expedition I've been involved with since 2012. And I've been working at this for a long time, although not as long as this photograph might suggest. This photo was done in the style of old-time Western copper plate photography. And a lot of my research of the last couple decades has specifically looked not merely at the biology of carnivorous dinosaurs like tyrannosaurs, but specifically on how that ecology and behavior changed throughout their life cycle. Now, Tyrannosaurus rex is by far the most famous dinosaur species, and even more specifically, the most famous carnivorous dinosaur. But in fact, it's just one member, although the last and largest, of a larger family of carnivorous dinosaurs, collectively called the Tyrannosauridae, which is literally the family of Tyrannosaurus. And quite frankly, to most of the public, and indeed to most of my colleagues who aren't Tyrannosaur specialists, they would have a hard time telling these guys apart from each other. So they're all very similar. So they are a group that's present in Asia and North America in the last 15 million years or so of the age of dinosaurs. And they are all characterized by the things that you probably think are just Tyrannosaurus features, like giant head, tiny little arms, long, powerful legs, and so forth. In fact, a lot of my earlier research, and still ongoing in this aspect, has been placing where the Tyrannosaurids, these guys here, fit in among the family tree of carnivorous dinosaurs. And thankfully, in the last couple decades, we filled in a lot of the gaps in this region, which we previously didn't know, which track the transformation of this group over time, where we see, for instance, an increasing emphasis on the skull as the way to kill and dismember prey. A decreasing forelimb function. The ancestors of the Tyrannosaurids had long, slender arms with grasping hands, but later ones, as we'll see, have these dinky little arms. And also something that's less well appreciated, and in fact, something I did my dissertation research on, is that these later forms are more specialized with regard to cursorial ability, that is, running in the broad sense. Although, as we'll see, running adaptations and speed adaptations are not necessarily the same thing. So here's the family tree scaled against geologic time, sort of an odd way. It's tipped on its side. So the asteroid collision is right down here. The beginning of the Cretaceous period over here, the Jurassic, so the age of Stegosaurus and Brontosaurus and Allosaurus right there. So we see there's a bunch of small, typically small, long-armed tyrannosaurs early on, part of a larger group of typically small-bodied, long-armed meat eaters. And then it's in the later part of the Cretaceous that we get the Tyrannosaurids and their immediate kin, which were much larger, which had the dinky little arms and these specialized running legs. Now, when the Tyrannosaurids were around, the world had a very different configuration than it is today. The supercontinent of Pangaea, which was present at the beginning of the age of dinosaurs, had broken apart. And more than that, sea levels reached their peak right about the point when the Tyrannosaurids were first evolving. And so in many ways, the world was more separated geographically at the time of the Tyrannosaurids. So just to orient you, Maryland is right about here on the coast of this microcontinent or subcontinent of Appalachia. Tyrannosaurus rex and its kin are here in Western North America and in Eastern Asia. In fact, let me just put that on there. This made a subcontinent called Asia America. So Asia over here, and then connecting over the Bering Straits, or what is today the Bering Straits, a peninsula coming down that represents what we call Laramidia, which is our name for the subcontinent on the western half of North America. And the dinosaurs of Asia America are extremely well known. We have spectacular sites from both Asia and North America with relatively complete fossils of all these groups. Consequently, these are very familiar animals because they're well known. So it's not just the Tyrannosaurids, but the horned dinosaurs like Triceratops, the duck-billed dinosaurs, this is their greatest range of diversity, the dome heads like Pachycephalosaurus, the club-tailed armored dinosaurs, those all characterize the Asia American community. On this eastern part of North America and what's referred to as the subcontinent of Appalachia, we had primitive cousins of the Tyrannosaurids, a group called the Dryptosaurids, as well as some hadrosaurids and a handful of other forms. We don't have as many good fossil sites for a number of reasons over here, but at present, no evidence that the true Tyrannosaurids were present here. Now, in the rest of the world, it's a very different batch of dinosaurs. It's not the Tyrannosaurids or their cousins that are the top predators, but another group of stump-armed predators called the Ballerinas. And instead of this huge diversity of beaked dinosaurs in these other regions, it's still the long-necked plant eaters that are the dominant. There are some of these beaked dinosaurs. They're just not as important as they are in the southern continents and in Europe as they are in Western North America, Asia, or even here in the East. Now, as I said, I've been looking at the transformations in terms of not just the origins of Tyrannosaurids from non-Tyrannosaurids, but in the life cycle of tyrannosaurs from their young forms. And so these are teenagers represented here versus a fully grown form. And I just want to point out here, these are reconstructions. Now, we still don't know many aspects about them, like specific issues of color, how common fuzz might have been on the body. We don't know. We know that tyrannosaurs were likely mostly not fuzzy, but we don't know that they're 100% not fuzzy. It's just an attempt by an artist to create an effective looking drawing. And this shows the very different proportions, that as it turns out, very different lifestyles of youngsters and adults. Of course, what we really have for the most part are the skeletons. So this shows the snout, the upper jawbone called the maxilla of a very young Tyrannosaurus. So by the way, 10 centimeters, that's almost exactly 4 inches. That gives you a sense of that. Versus the same bone from a very large individual. And this is a reconstruction of the skull of that little one compared to the skull of that big one. Incidentally, both these specimens found relatively close to each other in Saskatchewan. Now, dinosaurs, as we'll see in more detail coming up, went through a huge amount of size change between hatching and adulthood, far more than we see in big mammals of the modern world. And the little forms don't look exactly like the later forms. And consequently, some paleontologists have had a tendency to consider the small forms as separate species, distinct groups from the adult forms, and made a bunch of names for these different styles and different sizes of individuals. For instance, in 1955, the first of the Soviet expeditions to Mongolia, through the results of that, Melyev, the paleontologist here, described a number of new tyrannosaurs from Mongolia, and he considered these separate species of different sizes. You see them scaled here with art by Ken Carpenter, paleontologist who works on tyrannosaurs, among other things. And he considered the little forms from what's called the Namek Formation as distinct species because they had more slender jaws, they had a higher tooth count, so more teeth in the jaws. The teeth themselves were more blade-like. The forelimbs had a different proportion compared to the body, and the hind limbs had different proportions compared to the body than the big ones. And here we can see the smaller individual compared to Efremov, the leader of the expeditions, after it had been mounted in Moscow. But then in 1965, Rojdestvensky, one of the great paleontologists of the Soviet Union, looked back at these specimens and said, no, you're not looking at these fossils like a biologist would. You're trying to be a little typological in your thinking. Remember, these are the remains of animals, and animals transform and they change and they transform through time. And he said, almost assuredly, the differences you're seeing are not differences of evolution, but differences of what we say is ontogeny, that is growth. And as a consequence, Rojdestvensky regarded them all as being the same species, and by following the specific rules of biological nomenclature, it winds up the species is called Tarbosaurus batar. And this is a more newly discovered, very young Tarbosaurus, about a 2-year-old, based on the growth rings of its bones. And this gives you a sense of the changes of size and of proportions between a young Tarbosaurus and an adult, and reflecting changes of shape between a 2.5-year-old to a 25-year-old individual. Now, it's not just Tarbosaurus. We're lucky enough to have some young dinosaurs found in North America. In fact, from the very same rocks that Tyrannosaurus rex are from. And we have the same story play out over here. These younger specimens tended to be called a separate species by some researchers. They call it Nanotyrannus lancensis. And they distinguish Nanotyrannus from Tyrannosaurus rex, which lives in the same formation, by more slender jaws, higher tooth count, more blade-like teeth, different forelimb proportions, and different hind limb proportions. That should sound familiar. And indeed, it is exactly the same set of differences that back in the 50s, people had used to distinguish young Tarbosaurus from adult Tarbosaurus. So basically, people making the same, what I would consider mistaken conclusions about changes. And I think the weight of the evidence shows that these supposed Nanotyrannus specimens are just young individuals of Tyrannosaurus rex. Now, we don't have any Tyrannosaur hatchlings yet, at least not in terms of good specimens. In 1970, a former colleague of mine passed away sort of at the beginning of the pandemic, Dale Russell, did this attempt to show a hatchling, a half-meter-long hatchling of a Tyrannosaur based on changes of proportions with the later stages. We think it probably is not that bad in terms of the proportions. There's another artist's attempt to show one. We do know that all dinosaurs come from very small eggs compared to the adults. So the largest known dinosaur eggs are about 2 to 4 liters. So picture a 2-liter bottle or 2 of those stuck together. Even if you're the size of a herd of elephants, like a giant titanosaur, you come from a little bitty egg. And so there's a lot of changes to go on. In fact, in the last couple of years, a few specimens of what might be hatchling or even embryonic tyrannosaur have been found. You might see a little bit of blue representing a lower jaw and a little bit of yellow representing a claw, and the presumed size of those individuals compared to an adult. So this gives us a sense of how small tyrannosaur hatchlings might be. And through the work of a number of researchers, and most especially my colleague Thomas Carr at Carthage College, has shown the anatomical transformations that a particular species, in this case Tyrannosaurus rex, goes through from a very young individual through adolescence up to a fully grown adult. And these transformations reflect changing aspects of ecology, as I hope to show. Now, there have been speculations that perhaps tyrannosaurs lived in packs. And if true, that would make the story that I'm going to explain, the hypotheses I'm going to talk about, a little different. In mammals, even big predatory mammals like lions or tigers or cheetahs and so forth, the offspring, stay with the mother until they're almost fully grown. And so the young really don't have to live too much on their own. They're provisioned by their parents first with milk, and then eventually with the parents hunting and teaching the offspring how to hunt, until eventually the young go off and live on their own. You've probably seen documentaries, nature shows that take through the life stages of a particular family of cheetahs or something. Some people have speculated that tyrannosaurs and other meat eaters did that, but the evidence isn't incredibly strong. And instead, it looks more likely that tyrannosaurs, as indeed most dinosaurs, may have had parental care for at least several months. We see that today, for instance, in modern crocodilians. Here's a daddy gavial and some of his many babies hanging out with them, and they will stay with the parent for several months, but eventually they go off and live on their own. And because a little bitty baby gavial has a very different size and a very different shape and a very different strength, it's living in an extremely different fashion than its mighty father or mother. In this case, we know it's a father because of the mass at the end of the snout. And that's actually fairly common among reptiles that go through many different size changes throughout their life cycle. Here's another famous example, Komodo dragons. Komodo dragons are the largest living lizards in the modern world. And if you know anything about them, you know that they're large-bodied predators. They live in Indonesia. They're the top predator of the islands in Indonesia in which they're found. And they will kill goats and deer and buffalo and the occasional human. But that's only true as adults. They spend much more of their life cycle as little babies. And in fact, as babies, they're tree dwellers. They live up in the tree chasing insects and birds, looking out for their major predator being adult Komodo dragons. But eventually they change their role in the ecosystem. They change their niche. They come on the ground and become mid-sized predators and eventually change their role again to become large predators. And these might be better models than, say, a cheetah or a lion for how tyrannosaurs grew up. So how might their ecology have changed from youngsters to adults? That is, from ballerinas of doom, as I'll show, to bone-crushing bruisers. By the way, when I say tyrant in here, the name tyrannosaur is literally tyrant lizard. So they're nicknamed tyrant dinosaurs, or tyrants for short. So let's take that bone-crushing bruiser aspect. Tyrannosaurs are famous for having these extremely powerful skulls. And in some recent studies, various researchers have attempted to figure out exactly how powerful. One of the studies that I think is most effective is this one from a few years ago from a couple colleagues of mine, which incidentally has some of the lower values estimated for the bite force. And nevertheless, these are extremely powerful bites. They found that the bite force of an adult Tyrannosaurus generated something like 34.5 kilonewtons. That's almost 8,000 pounds. And more than twice the bite force of the largest living reptile, the saltwater crocodile of Australasia. By comparison, our bite force is only about 200 pounds. That's 0.89 kilonewtons. A spotted hyena, which is the strongest bite of any living mammal, is 4.5 kilonewtons. So, Tyrannosaurus does that and adds 30 more. This is about almost twice the bite force of a living great white shark. But even though I'm a Tyrannosaur chauvinist, I do have to say Tyrannosaurus did not have the strongest bite in Earth history. We know that there were extinct gigantic crocodilians that had a bite force about almost twice what Tyrannosaurus had. They had a much more solidly built skull, and otherwise it's about the same size. And the giant megalodon shark had a bite force truly tremendous, something like 108 to 180 kilonewtons, that is up to 40,000 pounds. Nevertheless, Tyrannosaurus had the strongest bite of any fully terrestrial animal studied so far, which is sufficient not merely to kill animals, but also to smash through their bones. This is a Smithsonian specimen of Tyrannosaurus biting onto the skull of a Triceratops in the new mound. We know these sorts of things happen because we have the specimens that show this sort of scalloping from a Tyrannosaurus biting not only through the meat, but through the bone itself. We even know that it's not just feeding on dead animals. There are Triceratops horns that have been discovered where we see the bite marks of a Tyrannosaurus that smashed through the horn, but the Triceratops got away, and there's traces of healing on that horn. So everyone who's ever played with a couple of plastic dinosaurs and had their Tyrannosaurus fight a Triceratops, we absolutely know that that happened on occasion. But of course, the goal wasn't really to fight, but to kill and then to dismember and digest. And in fact, we have the end product of this process. We have the coprolites. Those are fossilized feces of Tyrannosaurus rex, and they show the pulverized fragments of plant-eating dinosaur bones. So we do know that they smash through the meat and the bone and swallow them on. But those are from adults. Our estimate of the bite forces for younger individual tyrannosaurs through a number of different metrics is smaller. Now, it's nothing to sneeze at. The estimate of this smallish Tyrannosaurus individual is about 5.5 kilonewtons. That's still stronger than the bite of a spotted hyena, but nothing quite like the adult would be like. So the youngsters didn't have this bite that could smash through the flesh and bone as quickly in an adult. And by comparing the transformations in tyrannosaurs of various species throughout their life cycle, and then compared to other types of meat-eating dinosaurs, we see, although all meat-eating dinosaurs, whether non-tyrannosaurs or tyrannosaurs, obviously their bite strength increases as they get older. So this is body size on the bottom, or in this case, actual jaw length on the bottom, bite force over here. We see that the transformation in tyrannosaurs goes much more quickly. It really ramps up at about what the adolescent stage is for a tyrannosaur. Now, one of the other very famous things about tyrannosaurs is something that's not very strong in their case. It's something very small. It's the fact that they have tiny little forelimbs. And they truly are tiny. This is the original specimen of Tyrannosaurus. It's on display at the Carnegie Museum in Pittsburgh, and you could see literally those arms could not reach its jaws. It could not pick its teeth. It could not scratch its chin, and its jaws, its arms could barely clap with each other. And the fact this has been the butt of many jokes throughout the years. This was actually the very first, to my knowledge, tiny tyrannosaur arm joke from the Far Side, but these are just a fraction of the tyrannosaur short arm cartoons that I have. Some of them are even animated. It's worth noting that young tyrannosaurs, although their arms are still smallish compared to their ancestors, are proportionately a lot bigger than they are later on. So here we see the arms of this specimen called Jane. It's a young Tyrannosaurus. And we see that those arms are effectively longer. They could reach something, beyond their chest. This is the upper arm bone, the humerus of Jane. So an individual of about 1 ton mass. And that's compared to a 9-ton adult Tyrannosaurus. This is a specimen called Sue that you can see on display at the Field Museum in Chicago. So the arms of the adults are indeed bigger, but they are proportionately a lot smaller. So again, here we see one. It's smallish arms in the adults and much longer arms proportionately in the juvenile. The hind limbs transform as well. Tyrannosaurs, of course, are fully bipedal. They can only walk on their hind legs. And the hind limbs are some of our evidence for looking at running and locomotion in general in tyrannosaurs. Now, first thing I want to mention is that tyrannosaur feet are actually highly specialized. So these are non-tyrannosaur meat-eating dinosaurs. And in these two groups shown here, they're relatively broad feet. These are the metatarsals, the long bones of the feet. I should point out that all dinosaurs are walking on the balls of their feet, the way a cat or a dog or a chicken does. They're not walking with the soles of their feet parallel to the ground, like say we or a bear does. So in these forms, the feet are relatively broad, but in tyrannosaurs, the feet are relatively compressed and that middle bone is actually pinched out between the two side bones. Here it is in Gorgosaurus, here it is in Tarbosaurus. Tyrannosaurus would look very similar. In fact, here's a young Tyrannosaurus. Here's an even younger Tyrannosaurus foot. And those proportions, particularly in the young ones, are almost identical to the ostrich dinosaurs or ornithomimids. Now, if you've seen the original Jurassic Park movie, you know there's a sequence where a flock of dinosaurs called Ballerinas come running by the heroes of the story. That's an example of an ostrich dinosaur, of an ornithomimid. And they have exactly the same kind of foot structure as does a tyrannosaurid, and had long been recognized to be among the fastest of dinosaurs. And yet juvenile tyrannosaurs have identical leg proportions to large ostrich dinosaurs. So just a little reminder of anatomy. So there's the femur, that's the thigh. That's the tibia or shin, although we won't be taking much look at the tibia. And these are the metatarsals, the long bones of the foot. So if we plot the length of the long bones of the feet, the metatarsals, versus the femur length for a number of carnivorous dinosaurs, we see that the tyrannosaurs, who are in the orange squares, and the ostrich dinosaurs, who are in the blue circles here, the filled blue circles, they overlap in terms of proportion among the small carnivorous dinosaurs. And in comparison, big other carnivorous dinosaurs plot with much smaller feet. Now, having longer lower leg bones is an adaptation for increased speed, or at least increased running ability. Basically, you're covering more space with each stride. But a few years ago, a couple of colleagues of mine and me decided we wanted to study another aspect of locomotion, and that is agility. How agile might tyrannosaurs be? And how can we even approximate agility for a fossil creature? Well, we brought together experts from a number of fields of study to work on this. And our goal was to see how Tyrannosaurid, there's Tyrannosaurus rex with the asterisk there, compared to other big theropods, other big carnivorous dinosaurs. And what we were going to use was angular acceleration. So that is how much torque is being generated, how much pull is turning them compared to their rotational inertia, their resistance to being turned. So how can we estimate rotational inertia? Well, what we did is basically sliced a bunch of carnivorous dinosaurs like sausages, or rather, we took models, illustrations of this complete skeletons, or as complete as we can find them, with the muscles draped over them, of big carnivorous dinosaurs, and rendered them into a series of sausage slices. The technical term for sausage slices in terms of mathematics is a frustra. So these slices there, calculated the volume of each of these, then multiplied those volumes for likely densities in the different parts of the body, reflecting things like the percentage of bone versus muscle versus open space like lungs and air sacs versus guts and so forth, based on living relatives of dinosaurs. to figure out how the distribution of mass occurred over these bodies. Then we determined the torque based on the overall muscle attachment areas of the muscles from the ilium and the hip, and from the tail muscles that attach to the thigh, to the femur. And then we compared these values over body size to see which ones had increased turning versus decreased turning. And there's the math, don't worry, there's no quiz. And we found, shown here in blue, that tyrannosaurids at any given mass were more agile, had greater ability to turn the body against the resistance of the inertia with larger muscles and more compact bodies than other typical meat-eating dinosaurs. Now, it's true when we get, it's true with us as well. When we get to larger sizes, we may not be as agile as a teenager or a little kid. And it was true for dinosaurs as well. But even at this big size, a T-Rex is a much more agile animal than a comparable sized Giganotosaurus, for instance. But especially when we compare the adults to the youngsters, we see that the youngsters were indeed the ballerinas of doom that I referred to in the title. So tyrannosaurs could turn more quickly than other big theropods of comparable mass. That makes sense. They were probably hunting smaller, more agile animals. And in the case of, so tyrannosaurids could take advantage of their great agility because they're up against prey like duckbills and horned dinosaurs that were not the slow-moving clunkers of the Jurassic, the big long-necked sauropods or the heavy stegosaurs. Now, on the flip side, the more ancestral forms who were less able to turn quickly, they were perhaps a bit more stable. And when you're trying to eat a giant walking wall of meat, maybe you want stability over agility. But there's yet another aspect to locomotion we were interested in, and that was cost of transport and efficiency. So in a paper of ours that came out a couple of years ago, we looked at the cost of transport at different sizes among different types of carnivorous dinosaurs. And we found that for large-bodied carnivorous dinosaurs, the longer leg gave a slight increase in overall speed to shorter-legged forms. But what it really did was decrease the cost of transport. So it decreased the energy demands to cover longer distances. In contrast, for smaller animals, having a longer lower leg really does give you a marked difference in speed than shorter-legged forms. So as we like to refer to it from that paper, that for tiny theropods, the longer legs are for sprinting. But for giant meat eaters, the longer legs are for marathoners, covering more ground more efficiently than their shorter-legged ancestors. And so we see that many aspects in terms of feeding, in terms of forelimb use, in terms of speed and agility and efficiency are different in a young Tyrannosaurus versus a full-grown one. And that makes sense. A full-grown Tyrannosaur is going to be going after prey that itself is not particularly very fast. So these are shown to scale. Here's a giant duckbill, a triceratops, an armored ankylosaur. And if you're going to try to take these animals down as food, it's power that you want to emphasize. But a young Tyrannosaur is going to be too small to kill the big duckbills and the big horned dinosaurs. It's going to go after smaller prey. In fact, prey which are probably too small for the adult to go after. And speed and agility are more important here than bone-crushing ability. Now, I've also been interested in looking at a broader ecological issue of these changes that are particularly different between the age of Tyrannosaurs versus other points in dinosaur history. So these are the carnivorous dinosaurs, or rather members of the carnivorous dinosaur group, I should say, that are present with Tyrannosaurus rex. And we see a wide variety of them of different sizes, but it's worth noting that none of these forms are meat eaters. These are actually plant-eating, meat-eating dinosaurs or insect-eating, meat-eating dinosaurs. And I know that sounds strange, but think of a panda. A panda is a herbivore, but it's a member of a group that's called carnivora, the carnivorous mammals. And so when we look at a Tyrannosaur ecosystem, we have a huge giant predator, and then this extremely rare mid-sized one, and then more common small creatures, which are comparable to a human in length and smaller than a human in mass. And that's distinctly different than what we see at different points in dinosaur history, where we see other sizes of meat eaters throughout the ecosystem. And this was part of a multi-year research that I'd been working on actually since about 2004, finally got published last year. And at about the same time, I had colleagues who independently presented similar work. And in fact, I should point out that Kat Schrader actually successfully defended her dissertation at New Mexico was it just last week, 2 weeks ago. So yay, the new Dr. Schrader out there. So what I in particular was looking at was contrasting ecosystems with tyrannosaurids and additionally the southern hemisphere abelisaurids from the end of the Cretaceous versus those that were dominated by other types of meat eaters earlier in the history of the age of dinosaurs. And if we go to, say, a Jurassic ecosystem, we could find, in fact, even at a single quarry, we can see multiple sizes of meat eater that co-occur. And on here, only this one, and I should update this, arguably this one over here, are probably not meat eaters. So we actually do have meat eaters at many body sizes in between. And so it represents a difference in ecological guild strategy. So in ecology, a guild is a group that exploits the same class of environmental resources in a similar way. So we could think of on the Serengeti, the large mammal predatory guild. So these are the mammals that are feeding on medium to large size mammals. So they're not insectivores, they're not herbivores, etc. And so I did studies of ecosystems of carnivorous dinosaurs throughout the Jurassic period and the Cretaceous period, and was contrasting those in which tyrannosaurids were the dominant form versus those in which tyrannosaurids were not present. And my first primary question was, are the guilds in which tyrannosaurids are the largest carnivores actually distinct from the others? And what I was looking at were the distribution of sizes of the different carnivorous species in their adults, at least, in these formations. So these are tyrannosaur dominated formations. And we see they normally have one or two extremely large tyrannosaurid, relatively few, if in fact some cases no, intermediate sizes, and then a handful of small bodied forms. The crosshatch represents where there's members of Tyrannosauroidea, so Tyrannosauridae or their ancestors, but it doesn't actually come into the equation per se, into this analysis. This is simply tyrannosaur dominated communities versus ones in which tyrannosaurids were not the dominant forms. And here I think you could see there's a lot more intermediate sized forms. At least it appears to the naked eye. But of course, part of science is making sure that we actually test what might look to the naked eye as true, but may in fact not be statistically accurate. So what I looked at was counting the number of missing size classes among the adult meat-eating dinosaurs. And so there's 3 missing size classes here and no missing size classes here between the smallest and the largest. And it turns out statistically, Tyrannosaurid dominated communities, the tyrant communities, actually are confirmed to have more missing size classes than non-tyrant ones. And this is not just a matter of, say, undersampling. You know, we might think maybe we haven't looked at these tyrannosaur communities enough to pick up these medium-sized forms. In fact, the tyrannosaur-dominated communities include some of the very best sampled communities of dinosaurs in paleontology. And if we had the medium-sized forms, we would expect to find them. In contrast, some of these ones where we have almost no or no missing size classes between the smallest and the largest have only been worked for 1 or 2 field seasons. And yet in that time, people have picked out these intermediate forms. So a second hypothesis that was suggested, maybe the difference in size classes has to do with the presence or absence of the long-necked, or rather, and the total amount of prey in the community. So this is looking at the various types of dinosaurs, both carnivores and non-carnivores in the late Cretaceous, sorry, the late Jurassic of Western North America. So maybe there was a bigger smorgasbord for the non-tyrant communities, and that could afford more of these intermediate sizes. But in fact, when we plot them up, we see that there's not necessarily a big distinction of them, and we could check that statistically and find, in fact, there is no statistical difference in the amount of non-carnivores versus carnivores in the tyrant-dominated communities versus the non-tyrant dominated communities. So that's not the distinction. Now, some of my reviewers on the initial submission of the paper suggested maybe it's because sauropods were common in these non-tyrant dinosaur communities. They're present in some, but not most of the tyrant-dominated communities. Sauropods are the giant long-necked forms, and why might that be important? Well, just like tyrannosaurs, they had to go through a huge life cycle change in size. And that means you go from creatures that could fit in a soccer ball to animals bigger than a herd of elephants. So they run individually from Happy Meals to family bucket size. So maybe there's just a lot more meat on the hoof at that time. And it's true that sauropods are rare in most, not all, but most of the tyrant-dominated communities. And indeed, I did confirm that sauropod lacking communities are confirmed to have more missing size classes because those are all tyrant-dominated communities. And so that leads to an unsolved mystery. Which happened first? Was it that sauropods became extinct or rare in Asia America, their predators disappeared, and then the medium-sized forms with that? Or did the evolution of Tyrannosauridae succeed in wiping out the sauropods and the allosauroids where they were? And honestly, we don't know. The sampling there isn't very good. We have the precursors of tyrannosaurids at small body size at around that point when they were not the top predators, and we're seeing the origins of the major tyrant dinosaur prey at the same time. So regardless of how they got to this situation, I've hypothesized that the juvenile and subadult tyrannosaurids were effectively the mid-sized predators, that they were effectively different species ecologically than the adults. So here is a full-sized Gorgosaurus represented by the species here, but that smaller individuals, and these are actual skeletons of these mid-sized individuals, would have played different roles in that same ecosystem. And this might be an example of what's called niche assimilation, a term coined by my colleague Mike Brett-Sermon. Now, he used it to compare mammal communities and dinosaur communities. And as he pointed out, in a mammal community, like say the Serengeti, we can go from little dik-diks through antelopes and horses, zebras and so forth, all the way to the African elephant as different species of herbivore. But in the Hell Creek Formation, the end of the age of dinosaurs in Western North America, it's one species of herbivore, the duckbill Edmontosaurus, that can occupy all those same sizes. So this may explain why there appear to be fewer dinosaur species in a community than there are mammal species in an equivalent community. And so I took that idea and suggested that maybe tyrannosaurids had assimilated the niche that had been occupied by the mid-sized predators earlier in theropod history. And indeed, as my colleagues and I have been involved with have shown, there's more dramatic change in terms of bite forces, agility, speed, and endurance between young and adult tyrannosaurids than there are in other types of meat eaters through their growth cycle. And just to show that this is something that does happen in nature, just a reminder, here is in the life cycle of Komodo dragons, they change almost every aspect of their hunting, like what size prey they're going after, how fast they move, and their home range size as they go older. And sometimes there's rather dramatic shifts in there. Or if you look at alligators, the ones that get, after the parents have let them go, they're eating insects. Then at about 2 feet long, they start eating crustaceans and fish. And then they get to about 4 feet long, almost, they start adding mammals and turtles. So they're changing the part of the ecosystem that they're feeding on, and therefore their role in the ecosystem. And tyrannosaurs seem to have been doing the same. So tyrannosaurs are, to me, very interesting and exciting organisms. Plus, they can still help us, inform us about important things that we still need to remember in this day and age. So hopefully this gives you a little insight into some of the research and discoveries we've been making about this, in my opinion, wonderful group of extinct organisms. And I'm happy to take your questions. And let me stop sharing here for a moment. There we go.
Well, I'll let folks put their questions in the chat, but one of the first ones I have for you, Dr. Holtz, looks like, I mean, there's just so much research that you've done and colleagues of yours have done in the past, but when you look towards, the next 20, 30 years, what do you see as some of those potentially, big revelations or, big findings that could come from further research?
Sure. There's a number of them. One is simply to expand our search. That you might think that the world is totally explored, but it hasn't been in terms of research paleontology. We're still go out in the field. We still make new discoveries. There are time slices, so moments in time and space that we really don't know that much about in terms of the dinosaurs of the world. So filling in those gaps, for instance, that transition from an Allosaur dominated to a Tyrannosaur dominated Asia America, what's going on there? There's some sites that are intriguing, but we need to find the fossils there. But also new types of insights. Our ability to do CAT scans, especially micro CT, is getting better. And that can give us more information about things like the mechanical strength of bone or features on the inside of the skull where the brain case is and the sense organs that might be too fragile to mechanically prepared, but the CTs can reveal it just like a CT would for medical purposes. There are new insights being made in terms of chemical and isotopic paleontology, where we're sampling preserved biomolecules or the isotopic ratios in bone and teeth that give us information about the ecology of the organisms or their physiology. So we're coming in with new types of analytical techniques all the time. And in fact, that's one of the things when a totally new technique arises, some of us older people might not even know what questions they can answer, but young people who are working with this sort of approaches, they might be able to figure this out. I want to see a couple of things coming in on the chat. Every year or so, new species of dinosaurs discovered. And then the quote got cut off, but I'll say that in fact, I'm keeping a count of new species that have been named every year since 2003. And it's about 45 new Mesozoic dinosaur species every year. And so almost one a week on average. But as you're right, many species don't leave any fossil record. It might be that they lived in a part of the world where there wasn't sediment accumulating and therefore they couldn't become a fossil. Or the sediments did accumulate there, but it's not currently exposed, so we can't get to them. Or it did accumulate there and they were exposed, but they were exposed long before we were around and they've all eroded away. So sadly, we've lost a lot of material there, and we hope to sort of fill in those gaps. But there will always be a certain amount of the ancient past that we'll never know about. Let's see, did Tyrant's life cycle evolve based on their potential to occupy size niches that other species may otherwise occupy? In other words, were their earlier teen years extended so as not to compete with adults? Excellent question. And it does look, and I actually postulated this early on, it does look like that might be the case. That in the case of, first of all, tyrannosaurs have sort of a late onset of adolescence compared to a lot of dinosaurs. Like a duckbill is almost fully grown by about 7 or 8 years old, but a tyrannosaur has sort of a baby form or a youngster form to about age 11. And then it undergoes adolescence, which goes to about age 18. And then it's got its adult form. In fact, that curve sounds really familiar. It's like a human, except when you look at the mass size, that's rather different than us. So they have a sort of delayed phase of onset of adolescence. Also, the rate of change during adolescence is a lot faster than in other carnivorous dinosaurs. But the thing is, we don't have as many good life cycle restorations for the other carnivorous dinosaurs yet. That's still an area that is ongoing. So does size of body matter or adaptable mind? Well, in nature, in evolution, whatever works for you. Different strategies for different organisms. Obviously, like on our side of things, we primates, we don't have our greater brain power makes us vastly more effective predators than almost anything in the history of the planet. There's no way a human by themselves could take down a fully grown elephant. And yet, Stone Age peoples for the last several thousands, tens of thousands of years could take down the mightiest land animals that existed on the planet. And they did so by inventing tools, by coordinating with each other, and so forth. So in our case, having an adaptable mind is really efficient. But an amoeba is also extremely effective, and it has no mind. So it all depends. Whatever basically evolution and nature works for, whatever happens to work for you. Do we believe that T-Rex mostly hunted its prey or fed mainly on dead animals? Aha. Yeah, so that is a classic question. Was T-Rex a hunter or scavenger? The answer to the question is, was T-Rex a hunter or scavenger, is yes. It was a hunter or a scavenger. Almost no carnivore is just one or the other. And there is definite positive evidence that Tyrannosaurus fed on, bit and attacked living animals. But that doesn't preclude it eating carrion. And in fact, without being back in time in the field watching them, we wouldn't be able to know the percentage. And that's the sort of thing we need to know. Like if I were to ask most of you, what is more of a scavenger, a spotted hyena or a lion? Most of us would say a spotted hyena. But there are parts of Africa where the spotted hyenas kill more of their food than the lions in the same environment. But in other parts of Africa, those same two species, it's the other way around. So things in nature don't tend to be just one thing or just another thing to fit in neat categories. And it might be, for instance, different times of year, a Tyrannosaurus was more scavenger versus predator, different growth stages, etc. Let's see. Not sure if you can answer this yet, but did you serve as a consultant role for the upcoming Prehistoric Planet documentary series? Okay, so yeah, this is just, I'm not getting paid to do this. There is actually a couple new dinosaur documentaries after sort of a dearth for a while out there that are coming out soon. There's one that's on Apple TV called Prehistoric Planet. That one I did not work on. I had hoped to. I was contacted early on, but we didn't actually make the real connection on that. I'm really looking forward to that one. Additionally, there's a one-shot episode. It premieres this week in the BBC and about a month from now on Nova about the last days of the dinosaur. That one I did consult on with regard to the models, the CG models of the dinosaurs, mammals, and pterosaurs in that.
Well, Dr. Holtz, my last question for you was going to be, how can folks keep up with the great work that you're doing? So it sounds like that's one idea, but any others?
Sure. Well, you can follow me on Twitter. So I'm at Tom Holtz Paleo. In fact, I've got a screen here too. I could put this on. Let's see, share.
I'll share this out with everyone.
Okay,
too.
great. In the chat. So there's my website at the university. There is my Twitter handle, and I've got a YouTube channel. And specifically, so I use the tiny URL, so it's easier on tinyurl.com, Holtz YouTube with the H, Y, and T capitalized. And those are in the chat. And yeah, so specifically, you can check those out on my YouTube channel. I have links to public recorded lectures. So this one presumably will get in there eventually. I have links to some of my lectures from courses as well. So my Dinosaurs and Natural History class, you could go and see last year's lectures on that. And I'm in the middle of this, well, 2/3 of the way through my GL 204 course this year. I've been recording those. They're also available on there. And you can see in the chat the different links to those.
Wonderful. Well, we are just about time, so I don't want to take any more of your time, Dr. Holtz, but a huge thank you to you for sharing all of your wisdom and research and expertise with our alum. And I'm so grateful we had so many great questions in the chat from alum who were really interested in this. So huge thank you to you. And again, thanks to our alum who tuned in, who wanted to learn more from one of our super impressive faculty members on campus. So thanks again, everyone. Feel free to tune in to our next faculty series. It'll take place next week. But again, thanks, Dr. Holtz, and we'll see you soon.
Okay, take care and thanks for coming, everyone.
Bye.